Okie dokie. So we are now moving to something a little more efficient. So we are still solving systems of linear equations. And we have noticed, and we measured some runtimes and how long those can take. And we have noticed that basically Gauss elimination can be quite a long process. For some cases where I'm solving basically the number of systems of linear equations which all have the same matrix of coefficients A, we can do LU decomposition and save some time there. But other than that, it's a slow process because it takes what we say O, or order of n cubed floating point operations to solve a system. And however, our computers might appear really fast, but that's simply not cutting it for most of the problems that we want to solve. Further, whenever I have that many floating point operations, there's this round of error every time I both do the operation and store the result of that operation into finite memory of the computer. So that round of error, as we are kind of computing for a long time, will pile up, and that's a problem. So we need an alternative for larger systems of equations, and larger we roughly look at more than 1,000 by 1,000, systems that are more than 1,000 by 1,000 large. So one such alternative are so-called iterative methods. Basically, they're very similar in the procedure to root finding. Like I start with the guess, and then I go and try to improve that guess. And I'm hoping that if things are going well, in the numerical world we say converge, okay? If things are going well, I'm going to get closer and closer to the actual solution. I'm never going to get the exact solution, which with all of the round of errors in the world of numerical methods is not a big deal as long as I'm close enough. And I can control how close I get. Okay? So there's one of these iterative methods. Basically is literally the idea came about from rearranging my linear system. So if I look at this 4x4 system here, okay, so I have this is 4 unknowns, x1, x2, x3, x4. I'm looking for all those 4 that are satisfying these 4 equations. So if I rearrange things a little bit and basically leave x1 on left-hand side, put everything else on the right-hand side, from this equation, I leave x2 on left-hand side and put everything else on the other side. And same for x3 and x4. I'm going to get this type of system. This slightly reminds of that x is equal to g of x, if you remember, fixed point iteration for root finding. It's just now for a vector. So I have a vector on the left-hand side. It's all of its elements. In this case, 4, it could be anything, depending on the size of my system. And I have something that is a function of that same vector on the right-hand side. So question is, can I just actually start with any guess? Okay. I give myself initial x1, x2, x3, x4 to start with. 0 if I cannot think of anything else better. Okay. And then, based on these equations, I can compute my new guess. So I put my initial guess on the right-hand side instead of these x1, 2, 3, and 4. And then I get my new, on the left-hand side, I get my new iteration from the old one. And question, if I keep doing that, which is precisely what we are doing in fixed point iteration just with one number, if I keep doing that, am I going to get anywhere, right? So the answer, just like in fixed point method, is sometimes for specific systems, we can actually look at A and in certain case decide that that's going to be the case. It's going to work really well, and for some others, it's just going to be horrible, okay? But when it does work, it's going to shorten our time in looking for the solution quite a bit. Okay? So let's actually figure out a method. So it's called Jacobi's iterative method. If I assume an initial value, this is my vector, which is why I'm putting a superscript here. So this is my first iteration or 0th iteration, however you want to call the starting one. Then my next iteration I'm going to get by plugging that first iteration into this right-hand side and get my new iteration on the left-hand side. So in general, I can actually generalize this, that starting from some kth estimate, which is my initial estimate at the very beginning. This is my kth estimate. That's an entire vector. I'm going to get my next estimate, which I'm indicating as k plus 1, by basically plugging this in for all of the vector elements. And this here possibly looks a little intimidating, but this is these sums that we practiced initially. But it's really just writing this up in a more general form and for any size of a vector, n, not just necessarily 4. Does everybody see? So I have, for instance, first one, if my I is equal to 1, I have 1 over A11, B1 minus sum of all of the others. And sum of all of the others goes from 1 to n, and j is not equal to I, because that's already here. Aij xj. So in this case, it would be A1j xj for all of the j's, other than 1. Okay? So that's if I'm plugging in for I is equal to 1, I can do all the others. So everybody sees how this is a general version. So this is just generalized version of this. Why do I like generalized versions? So I can code for any n. So I can do this for n larger than 4. N larger than 4, I can play with on my own all I want. I want a computer to work with system larger than 1,000, right? N is equal to 1,000. So I can definitely not, I'm not going to play with directly plugging in these equations. I need something that is general. Awesome. So let's actually do an example. And first, let's do it by hand. Okay? So I'm going to give you a 3 by 3 example, which is much simpler. Pull out a piece of paper. So my system, which is 3 by 3, is here. And I want you to start from initial guess of 0, 0, 0. And using these formulas, here I gave 4 by 4. That's frankly because it's a scan from a textbook and they used 4 by 4. I didn't type it in myself. But you can just use these formulas, just delete everything that has 4 in there, and you're going to still get the same formulas. Or use this generic formula here. Either way, I want you to, by hand, get estimate number 1 from this 0th one. So essentially, I have x0 that is 0, 0, 0. So this is my x1, 0, x2, 0, x3, 0. I am wondering what is my x1, which is x1, 1, x2, 1, and x3, 1. So my next iteration of the entire vector. That's what I need. By hand. So before we program this, we need to do it by hand. If you're bored, you can find the next one, x of 2. And see how close do you actually get to the actual solution. So I gave you the actual solution as well. Okay. My thing has disconnected. Just a moment. Why? Okay. So what did we get? I'm gonna call this initial iteration x old. So my initial one is x old, or just x if you will. And question is, what is the next one? So based on this first equation, my next one I basically get by, or the first element I get by isolating this x1 and putting everything on the other side, right? So my x new first element is actually 0, is 7.85 minus, or that's actually plus 0.1 times x old of 1 and plus 0.2 times x old of 2. All of that divided by 3. Do we see how I got that from the first equation? And I could have just used this as a formula as well. So I'm just now calling it x old and new. If it's easier, I can call it x0, x1. What do you feel like? This works? Okay. And then my x new of 1, which is the second one, as I get from this equation. So it's minus 19.3 minus 0.1 times x old of 0 plus 0.3. I'm changing things as I move them to the left-hand side. X old of 2. And I'm dividing by that's multiplying 7x2, right? And then the third one, I basically leave this on the left-hand side, put everything else on the right-hand side, and I get my x nu of 2. So I'm using my Python now as a calculator before I switch to actually programming it a little more efficiently, and I divide by 10. Ooh, what did I do? Ah. Something else. X new. NP zeros of X old sheet. This is what I got. Did you get by hand something similar? So just to put notes, what am I doing here? Using Python as a calculator for 3 by 3 systems. So this is already not that bad. Look at this. The actual solution is actually 3 minus 2.5 and 7. I'm already in this first iteration, not that far away from 3, not that far away from minus 2.5, and not that far away from 7. It's pretty amazing when it works. Doesn't always converge. And I just started from a guess, like 0, 0, 0. How would I now go and proceed to calculate my next iteration? So all of my x news should become x old, or rather my x old should become x new, and then calculate x new again, right? Okay, so I'm gonna do that again by hand. X old of 0 is x new of 0. X old of 1 is x new of 1. X old of 2 is x new of 2. And then just really redo this. Good old cut, copy, paste. And print it again. Let's now see. I'm closer to my solution of 3 minus 2.5 and 7. How would I calculate relative error for this? I need to gauge how close I am to the solution. What would I do? So when I know exact solution, then I can actually just compare each of these against that exact solution. This is a vector. So technically, I can use one of the vector norms I know. L1, L2, or infinity. Which one really is the best? If I'm converging, I'm converging. If I'm not, which precise norm I'm using is not what's preventing me from finding the solution. Okay. So let's say L2 norm. So you could basically do L2 norm and see how far this is in absolute sense, just L2 norm of the difference, or relative sense, right? Divided by the actual L2 norm of the solution. If you know the solution, which if you know the solution, most of the time we don't need a numerical method to find it, right? So when we don't have exact solution, we will simply compare our last two guesses that we have and see whether they're getting closer and closer and closer to each other. Okay. So basically just to check on or to formalize a little what I just said. Okay. When are you done? You can find some epsilon in this iteration. Okay. Here I'm saying, hey, I could just pick a tolerance. So for every element, how close it is, and that it's less than certain epsilon away. I prefer actually using L1, L2, or L infinity norm, just to be more formal. This works too. Again, which particular norm? This is actually saying let your infinity, L infinity norm be less than tolerance. Okay? Because it's the worst case scenario is less than tolerance, then all of them are. So basically, which norm you use, it's not all that important as long as you're checking that you have this, that you are getting closer and closer in your solutions. And then you stop. And when you stop, what is your tolerance depends on you or whoever programmed this. So it could be 10 to the minus 3, it could be 10 to the minus 5, whatever it is that you come up with. You have to understand that this is just like in root finding, it's a choice you make. Okay? All right. So one thing is like, when is this going to actually work? Very similar to fixed point methods. There is a stricter, if you remember, absolute value of G prime had to be less than 1. There's an equivalent for that for these systems, and that is that basically diagonal elements in every row are larger in absolute value than sum of all of the others. In that case, this is not the only time it's going to converge, but in that case, we actually know it will. What means here is that 3 is larger in absolute value than 0.1 plus 0.2, which it is. 3 is larger than 0.3. 7 is larger than 0.4. And 10 is larger than 0.5. Obviously, this has been designed to be very diagonally dominant. And in this case, it's going to converge. And we actually already see that even in 2 iterations, I'm getting pretty close. Excellent. So you know when to stop. You know how to design things. So now I would like you to create a function, Jacobi iterations, that takes my A, B, some sort of initial guess. You can call it X old because that's what we were, or X0, however you want to call it, and some tolerance, and then perform Jacobi iteration until that tolerance is met. And you can use this system as a test system, right? And Ningyu and I will move around to see that you have completed this. And this is going to be one of those things that you will submit by Wednesday. So, function, Jacobi iteration. You can, first thing first, you can always define a function with the appropriate name, appropriate input, and what it returns. Okay, and that's your sort of shell that you're filling in. Mm-hmm. This slide?
No, the Python Jupyter.
Mm-hmm. Let me just move the slide so everything is visible. So this is basically the shell of the function, right? And you can get motivated by what we wrote down here, but these do need to be loops now. And raise your hand if you need help. This was just using it as a so now you need loops to define all of these. This is a useful thing that I'm going to copy. But, no. If you're stuck, here are some questions to ponder. Or certain things that you can work on. $5 please. But again, just use the generic formula because now you need it to work for general n.
Oh, there it is.
Use this. Typing in a little bit.
I'm still trying to get that first part.
This is what I said, then we just repeat this. So this was just doing 2 iterations. So this is the second iteration. So if you were doing things by hand, this is what you would type in. Calculator. So first you have the first guess. This is just making numbers and that I'm giving you the same array, the same size. This gives me zeros and the same as this. So now I compute for 6 this array by rearranging and redo the computation, then I have to replace this old value with this new values and just repeat it. That's because of the two iterations. So those are my two iterations. So this was just doing like stupid. Now I want to do that in a process that works for these size. So first when I'm coming in and saying, hey, allow me this X new, so I'm going to basically repeat the same as this. Right? Just give me a vector of the same size. That would be cool. So that's the first line. After that, I want things to work on the same size. I can either figure out what's the size of this A or whatever it is, I need a number of equations. So that's what I'm doing with n comma n is a without change. M should be the same as n, actually. And if it's not, I have a problem, but I'm not checking for that.
What is T allow? Yeah.
Tolerance. So that's the tolerance until I need to iterate. So basically my error has to be less than tolerance, right? And now I need to reconnect. Okay. I'm trying to connect, just a moment.
Sometimes the computer has its own rationale.
It tells me code 1028. I type in 1028. It tells me it's incorrect. Okay, dismiss. It is 1028.
1028.
Yeah, that's what I'm trying.
1028. Maybe it's because of the caps.
It's no, I'm typing it 1028 and it says incorrect code. Okay, once again, I'm gonna close everything down.
Guest, you are connected to guest?
No, this time, no, but let's go off and on. Like this has apparently changed, but it's not really acknowledging it that here. It's just not. And now it's you to guess. I need to delete that network from my. Because when it's on UTGuest, it doesn't even allow me to. It's UTexas. Thank you. But not, look at this.
Retreat.
Off, on. That's gonna restart it, I hope.
No.
No?
Did you type in the correct address of the classroom?
That's the classroom. I don't have to. I'm using this every day. I just use it.
Yes, it is. Some
Because when I type in that thing, all right, I'm just gonna walk around. This is not gonna connect. So first things first, you have 3 of them. This is X of I. This is gonna work only for this 3x3 system, but we want it to work for everything. This is your I minus some sort of magical sum and divided by A. That's the formula. And we need another formula for sum. Yes? So let's program this for loop. Yeah, let's program this for loop, and this is just the end. And then this you could do this also in another for loop. Not 3 of them. You don't know whether it's 3, it's n. Well, let's try it out. No. Oh, okay. Anybody else think so? Because this is not connecting, so.
Let's see what we did so far. This is
Okay, so first things first. So yes, this is fine. You just need this kind of programmed in a more general case.
The JacobiIteration only works for
Yes.
just wants to program
Yes.
this.
And
We
this
cannot.
I'm gonna call this some sort of magical sum. Yes, so once you
I'm trying to generalize.
then it's new with this. Okay, so now let's, and this is all working for every. You don't need this. Every time. So now I have this way. Yes, this, except this is all great. We do not want to include when j is equal to y. So just say if jj, how do I say it different from I?
It's great.
It's good. You have to go to web to understand it.
No. How do I say j is different from I in Python? Exclamation equals.
Exclamation.
Equals.
From I. So J equals from I.
And then magical I. Let's do another. Or at least you program those loops. Now there's just calculating the error. Okay. I will issue tonight a short video with pointers of how to do this, but I do expect you to complete it by Wednesday, okay? But try alone first.
For the project, how's that?
So project, did everybody sign up for projects?
Yes.
Okay. Those who did not will get a warning today.